Okay, so we have 10 people joined. Am I audible? First of all.
Yes, sir. Yes,
Okay.
sir.
Okay, so let's start. I'll share my screen. Give me a moment. Is this visible?
Yes, sir.
Yeah. So, hi, my name is Arch, and so this is going to be our 2 hour weekly session for this NPTEL course on classical mechanics. I am a PhD student at IIT Bombay and I am also a PMRF fellow. So, part of fellowship, we have this collaboration with NPTEL wherein we are supposed to help students of whoever has taken the course in whatever way, in whatever capacity we can. And these 2 hour sessions are part of it. So, this is my email ID in case if you want to contact me, you can contact me through this. Uh, these are basic rules of the game that we are going to play every week. Every Tuesday we'll meet from 6 to 8 p.m. and that will go on for 12 weeks. Uh, and the nature of interaction is going to be two-way and somewhat more informal. Which means you can interrupt me, you can ask questions, and this is not professor teaching and student learning. And by NEP, I mean National Education Policy. It says that education should be student centric, not teacher centric. So let's try to have as much conversation as possible. The language of this session is primarily going to be English, but during Q&A, if you want to ask question in any other language, you can, provided there is someone who can translate it to English so that everyone can understand. In case of Hindi, I myself can understand, so I will be able to translate it. So आप हिंदी में पूछ सकते हैं. For other languages, make sure there is someone you know who can translate it to English. And when can you interrupt to ask me any question? Anytime. And this is very informal. And the videos of these sessions will be uploaded for your future references as well as those who miss for some reason. Maybe some people are busy this time. So they will be uploaded to this YouTube channel. And the slides of these sessions will be on a Google Drive folder. And the last one is that there is this code: rules and records are meant to be broken. So in that order, first you break rules, then you can break records. So all these rules and everything is flexible. So these two are the YouTube channel QR code and Google Drive QR code. You can take a screenshot and then you can for your future references. So any questions regarding this? Anyone?
No,
Okay, then
no, sir.
yeah. So let's go ahead. My name is Arsh. You can call by my name also. That is also fine. I'm just like you, a student. So structure of the session is going to be. This is what we are informed. We have to solve previous year's assignment solutions. This is what NPTEL team has told me. And then we will do doubt solving session and general interaction session, so you can ask any questions that you had but couldn't ask the professor because it was pre-recorded video. And if you have any other suggestion to add for these sessions, you can ask. Okay, so if not, then we'll start with week one assignment. These are previous year's assignment questions in 2022 or sorry 2020. So there might be some similarity, but some questions may be different. And so we'll solve one by one. So the first question is, by the way, I hope everyone has gone through the lecture videos for the first
Yes.
week. Yeah. So the first week is pretty introductory. So are the assignment questions. So first is, how many degrees of freedom does a particle moving on a circle have? So we have a circle, and a circle is actually is part of 2D space, but it is a one-dimensional curve. So if particle is moving along this, then we just need to specify the distance it has moved from, say, some reference point. Or alternatively, we can just say the angle traversed by it, and that will also serve as a coordinate of the system. So we just need just one number, and therefore the particle has 1 degree of freedom. Okay, let's go to number 2. How many degrees of freedom does a particle have when it is constrained to move on a sphere? On a sphere. So a sphere is a, sorry, oops, yeah. So sphere in itself is a 3D construct, but we are supposed to move on the surface. Now surface, first of all, intuitively, intuitively, it's 2D, right? Secondly, if you want to prove why it is 2D or why does it have 2 degrees of freedom, you can think of as one coordinate being the latitude of the point and another coordinate being this, how this angular distance from some plane, great plane, that is the longitude, right? This phi. So you can specify latitude and longitude, and then you exactly know where you are in the space. This means the particle has only 2 degrees of freedom. Okay. How many degrees of freedom does a diatomic molecule? Now, so we have two atoms and they are joined. But do we know the distance between them? No, like the bond length is not given. It need not be a fixed number. We all know that bonds actually vibrate, right? If we have, let's say, carbon monoxide, the bond distance between the distance between them, that is the bond length, can change. So as far as we are concerned, there is no constraint between them. Maybe they cannot go very far away or cannot go very near, but this distance need not be fixed. Need not be. Which means this can have its own xyz, and then this can have its own x2, y2, and z2. And there is no constraint as such. So in total we have 6 degrees of freedom. Okay. The fourth is more technical or mathematical. Surface is given by this equation: x plus 2y plus 3z is equal to 0. Which of the following vector is parallel to the normal to the surface? So we have learned in the lectures that if surface is given in the form of phi of xyz is equal to 0, there is no time dependence, then the normal would have, so on the surface you have d phi is equal to 0. So in our case, phi is x plus 2y plus 3z, right? Then d phi becomes dx plus 2 dy plus 3 dz. is equal to 0, and then this we can write as grade phi dot dr. Is that correct? Yeah. Then so dr is dx, dy, and dz, right? And what is grade phi? Grade phi is 1. With respect to x we get 1, with respect to y we get 2, with respect to z we get 3. So this grade phi is the normal, because the gradient shows the direction in which the phi is changing the highest, and it always changes the highest in its direction of the gradient. That's why it's called gradient. If you put a ball somewhere, it will go in the direction of the gradient of the potential energy. So this means the gradient is 1 comma 2 comma 3. In vector notation it is x plus 2y plus 3z cat. Okay, so the answer becomes this. Now we should, okay, the question is solved, but we should make a general connection that whenever there is this, uh, this is a linear equation, right? So whenever we have a linear equation in 3D, it means for one, it's a plane. In general, it's a hyperplane in n dimension, and the coefficients of x, y, z are the coefficients of this normal. Okay, so this is something that we can keep in mind, and note that this is independent of x, y, z, which means it is in the same direction everywhere, which means the surface has to be a plane, which it, of course it is, as we can see. So now the questions are for indices, playing with indices and using Einstein's summation convention. So are you guys familiar with Einstein's summation convention?
No.
Okay.
Yes, I am.
Okay. Some of you are, some of you are not. So better to first revise that. What does Einstein's summation convention mean? It means repeated indices. Indices are summed over. So, as you must have noticed around you, all the creative people are also mostly lazy people. And Einstein, of course, was creative, so he was also a lazy person. What he noticed was many times in his calculation, he would have to write sum over a is equal to 1 to 3 xa ya, something like that. So he said, why not I just write xa and ya, and then I will just understand, because there are two, because the a is appearing twice, it is implied that it is summed over from 1 to whatever dimension it is. So that is called summation convention. So let's take this example. Delta k by definition means which index is repeated, so that is k. So k will be summed over from 1 to 3. 1 to 3 is given, delta k. Now it's easy, which means if we expand the sum, it's delta 1 1 plus delta 2 2 plus delta 3 3. I have just replaced k by 1, 2 and 3. So delta 1 1 is 1 because, oops, yeah. So delta 1 1 is 1 because both these indexes should be equal for this delta function to be 1, otherwise it's 0. Same, delta 2 2 is, sorry, 1, and delta 3 3 is also 1. So the sum is 3. So,
Can you explain again?
sure. So, did you understand the rule, summation convention?
Uh, Partly.
Partly. Okay. So, what Einstein says is, if you see two indexes, any indexes, anywhere, let's say there is some star with index 5, and there is another symbol, whatever it is, and another again 5. So, if this were not 5, then it is just a symbol. But because there are two phi's here, we have to assume that it is actually defined as sum over all phi, then whatever it is. So just because we don't have to write this every time, we just omit it and say that Einstein's summation convention is implied. This just saves our ink, time, and clarity of thought. So,
Okay.
okay. Now here delta k in this k is the index that is repeated, which means k has to be summed over. This is definition. Okay. This is defined to be this way. And then when you sum, it's just a simple mechanical process. First replace k by 1, so that will give you delta 1 1. Now put k is equal to 2, so you get delta 2 2, and put k is equal to 3, so you get delta 3 3. And delta function you should know, delta ij would be 1 if I is equal to j, and is 0 if I not equal to j. So this is definition of delta function. In case you don't know, say if basically it says that indexes should be same, only then it is non-zero 1. Okay.
Okay.
Okay. Yeah. So
Is this one?
yes,
Isn't this a Kronecker delta? Delta function is
yes. This is called Kronecker delta.
like the delta function I know is the integral runs from minus infinity to infinity and zero
So
zero.
both are related. This is the discrete version of that delta function, Dirac delta function. You mean, right?
Okay.
Yeah. So Dirac delta function is in differential form. This is discrete form. I think as the course runs, we will encounter Dirac delta function also. So we'll cross that bridge when we come to it. Okay. Again, another exercise, same thing, Einstein summation convention. And in this case, we are given delta jk. Again, by definition, which index is being summed over, j or k?
J. Okay.
Yeah, both j and k are
J.
repeated, right?
Yes.
Yeah, so then we have to sum over both j and k. From 1 to 3, delta j k, delta j k. This is definition. Okay, sorry. Yeah. Now again, so we can expand this out. This will have, if you expand this k term, for each j we will have 3 terms, and then again j itself has 3 values. So in total there will be 9 terms. But we just want to know when it is non-zero. That will be only when j is equal to k, right? Because in
Yes.
delta function we have j and k. So that means only when j is equal to k, and then j runs from 1 to 3, delta uh, jk. Yeah. And when j is equal to k, this is equal to 1. So we have 3 times 1. So again we'll get 3. Is that okay?
But there are two delta JK, right? Multiplied there.
Yeah, so there are two delta J. Okay, so you are saying I should put ideally square. Yeah, you are right.
Yes.
Yeah, yeah. But it's either 0 or 1, so squaring it doesn't matter. Still 1. But you are right. I can write like this. Okay.
Okay.
Yeah. So the answer would be 3. But as a general note, we can say slightly something more. Or you can think about it. If we have a matrix, let's say A, and its components are Aij, and then I multiply it with delta I, what would we what would it give? You can think about it and maybe tell me after this session or during the next session. Does it give some property of A? That's the question.
Identity,
Sorry, can you repeat?
identity matrix.
It will give identity matrix. Okay. Just think about it. Uh,
It will give the diagonal elements of the matrix A.
it cannot because it's just a number, right? There is no free index. So there are indices which are repeated. Those are called dummy indices because we are just summing over them, and those
I
which are
mean,
not.
not
Yeah,
it will give the sum of the diagonal elements. So it will basically give the trace of the matrix A.
yeah. So this will give trace of the matrix. That is correct. Excellent. So now we can again think of this question. Let's say first, this is basically our identity matrix, right? Because identity matrix JK element would be delta JK, and then you can think of multiplying it again. So what this entire thing gives is trace of identity matrix, which we know is 3 because it's 1 plus 1 plus 1. So what I want to say now is that there are multiple ways of solving questions. There are multiple perspectives of looking at the questions, and these ways actually help us build this intuition about the subject. So we should try to solve it in as many ways as possible. Okay. Another question with indices. Now we have another animal that is called Levi-Civita antisymmetric tensor. Have you heard of it? Have you used it anywhere?
No.
Okay. So
Yes.
so let's first define what epsilon ijk would mean. First of all, ijk run from 1 to 3. So in total, it will have 3 into 3 into 3, 27 entries, right? Any 3 cross 3 cross 3 tensor would have 27 entries. The epsilon 1 2 3 is plus 1, and so is any permutation of 1 2 3. By permutation, I mean, let's say we are going from 1 to 3. So I can start this cycle from anywhere. If I start from 1, it becomes 1 2 3. But I can start from 2 also. Then it would become epsilon 2 3 1. Then it's also 1. Or I can start with 3. Then it becomes 3 1 2. So epsilon 3 1 2 would be plus 1. But if you go in a reverse order, that is 1 3 2, epsilon 1 3 2, then it would be minus 1. Epsilon, then I can start with 2 2 1 3, then it's minus 1. Epsilon, then I can start with 3 3 2 1, that would be minus 1. And any other, how many entries are remaining. 21 entries are 0. So basically, these 6 are the only entries where all the indices are different, right? You can have 1, 2, 3, only 6 permutations, 3 factorial. So in anything, let's say epsilon 2, 2, 3, that would be 0. So if two indices are equal, if two indices are equal, epsilon becomes 0. So this is how this Levi-Civita symmetric anti-symmetric tensor is defined. This is the definition. Okay. Now let's look at the the expression epsilon I j k and delta j k. First of all, which indices will be summed over? J and k, right? Because those two are being repeated. So I have j running from 1 to 3 and k running from 1 to 3. Epsilon I j k delta j k. Okay. Then we know that either delta jk is 1 or 0. So when it is 0, the term just vanishes, right? So it means j has to be equal to k, right? And then j runs from 1 to 3, epsilon I jk and delta jk. But when j is equal to k, this epsilon would be 0 by this rule, right? So j is equal to k implies epsilon is equal to 0. So in a way, these two are like enemies because delta wants j and k to be equal, but epsilon wants everything to be unequal. So when they are multiplied, it is guaranteed that at least one of them is 0, which means the sum will be also 0. So the correct answer is 0. Okay. On more abstract level, if you have learned group theory, etc., you can see that this is antisymmetric and this is symmetric. So when you switch j and k, the delta remains the same. Delta jk is equal to delta kj, but epsilon ijk and epsilon ikj are negatives. So this entire thing has to be antisymmetric. And then when you sum an antisymmetric thing over the indices which make it antisymmetric, then you get 0 answer. So that is somewhat more advanced, but the straightforward calculation will also give you 0 as we show. So now, okay. Next question is about generalized coordinate. This is a good question because basically checks our understanding that we have one coordinate, generalized coordinate qy, and another is qj. So if I not equal to j, then we know qy and qj are independent, right? That's what generalized coordinates mean. They can be independent. If I give you q1, you don't know what q2 is. You have to tell me. Are independent, which means delta qy by delta qj is equal to 0. However, if I is equal to j, then qi and qj are same, right? Let's say they are 3, then q3 same as q3, whatever it is. In that case, let's say it's delta q, let's call it q. Then it is just delta q by delta q, which is obviously 1. So what we got was if I not equal to j, it's 0. If I equal to j, it's 1. Now, do we know of anything that looks like that?
Delta Ij.
Any function? Yeah, exactly. This is delta ij, because delta ij also behaves like this. When I not equal to j, it's 0. When I is equal to j, it's 1. So this means this is equal to delta ij. But this we could do only because these are generalized coordinates. This may not be true for x, y, or Cartesian coordinates, and which is why we write things, we expand it in terms of generalized coordinates, then we proceed to write our Lagrangian in generalized coordinates. So this is the reason. Okay, next one. Again, qi's are generalized coordinates, and the quantity is del qi qj on del qk. This q should be slightly bigger, maybe typo. Okay. So again, same thing. We are differentiating with respect to qk. So if I not equal to k and j not equal to k, then qi qk are independent and qj qk also are also independent, right? It means the answer would be 0. But if I is equal to k, let's say, then what will happen? Then we have del qk qj divided by del qk, and this will be equal to, we can take out qk times del qj del qk plus del qk by del qk times qj. This is equal to 0. Let's say j is not equal to k. Okay, but this is equal to 1, so we get qj, right? Okay, and by the same logic, I could have j is equal to k but I not equal to k. Then what will I get? I got, in this case I got qj, so in this case I will get
Qi.
y, right? So let's try to write this in terms of delta function. It says if I is equal to k, which means delta ik. Delta ik means, basically in language of logic, delta ik means if I is equal to k, then you do, then it is 1, so it's true. So into qj, right? If I is equal to k, you get qj, plus if j is equal to k, you get qi. So if j is equal to k, you get qi. Okay. Do we have anything that resembles like this?
Option first.
First option, right? It's written in the reverse order, but it's the same thing. Okay. So that's one thing. Yes, we have solved. Another thing, we can check whether this case is correct or not. So if I not equal to k and j not equal to k, then this both are 0, right? So again, it turns out to be 0, so it is correct. And then we can see the last case, when I is equal to k and j is equal to k. This is the fourth case. I'll say 3, 2, 1. In that case, both of them would be 1, right? And then you will have qj plus qi, but j and I are same thing because both are equal to k. So in that case, the answer you get from this is 2qi, or you can say j or k. All of them are equal. But does it happen? Of course it happens, because our thing is now qi square, because I and j are equal, and upon del qi. So this is like derivative of x square. So you get 2qi. So it checks out all the cases, and we can be sure this is the answer. But now we can be somewhat smarter. If we wanted to, let's say, solve this in gate or net, if we already knew this answer, then we can be blind to all this expansion and everything, and we can just treat this as some variables. So if I can write this as del qi upon del qk times qj plus uh, qi times del qj upon del qk chain rule, and this I know is delta ik from the previous thing. So it's delta ik times qj plus this is delta jk qi, and then we have our answer without thinking any of this. Both methods are correct, but first is, you know we climbed the ladder. We first saw this question. Now if we remember this, then this becomes easy. So now we can see the steps, we can see the structures to these problems. So this is one way you can solve. Okay, so let me proceed. Okay, in this uh, j is equal to same as previous thing, but j is equal to I is already given. So in the previous one, whatever we got, if we put j is equal to I, then it becomes this one. So in previous thing we had delta, sorry, delta jkqi, delta jkqi. I am writing previous answer plus delta ikqj, right? Now put, because we had qj in previous question instead of this. So put qj is equal to qi, or j is equal to I basically. So this answer will become delta I k qi plus delta I k qi. So it becomes 2qi delta I k, which is not in this one of the options. So where did I go wrong?
We can directly multiply qi into qi.
Uh-huh.
So it becomes delta qi squared by delta qk.
Oh, okay. Delta qi square by delta qk, right? Okay. Then
Now if I is equal to, now we can directly take the derivative. So it becomes 2qi.
2qi del qi by del qk. Is that correct?
Yes, and if I is equal to k, then del qi by del qk is 1. So it
So
becomes 2qi.
2qi delta ik, right? I is equal to k is not given.
If it is not, then it's 0.
Yeah, but that is not in the option. We have to select, and one of them is correct. Trust me. Can anyone resolve this?
The Einstein summation is implied.
Sorry?
The Einstein summation is implied here. So
Yes, exactly. So we are treating I as if it's a free variable, but I is actually repeated twice. See, that's why they didn't write qi squared. Although it means the same thing, but when we write qi square, it could mean that just for one I. But we have to sum over all I. So when you sum over all I, you have q1. Let's just explicitly write q1 1k plus delta q2 delta 2k and 2q3 delta 3k. Now, no matter what is the value of k, one of them would be would be non-zero, 1. Let's say if k is equal to 2, then this would be 1 and this would be 0, right? So, whatever the value of k is there, that will be the answer. So, in this case, it becomes 2q2. If k was 1, answer would be 2q1. So basically delta ik forces I to be k. Okay. So again to put I is equal to k. Basically we are forcing I to be equal to k. So this becomes 2uk. Okay. Keep. So these were the 10 questions from the previous years. Now the ball is in your court. You can ask me any question. First of all, did everyone understand the discussion so far? Yeah.
Yes, I did.
Okay. So if anyone has an, let me see the textbooks. Okay. During the when I'm solving, I cannot see the what you type. So you will have to speak. Sorry. Okay. So now if you have any questions, not just regarding your assignment, but in the course in general, you can ask me.
I have
So for the course, are we following the Goldstein textbook for classical mechanics, or is it something else?
So as far as I remember, Professor mentions Goldstein to be one of the reference books, but it is not the reference book. So I don't think there is one book that is being followed. But yes, Goldstein is one of them, so you can look at.
Okay, sure. Thank you.
Just a few other books.
Harish, you are not audible. I think you will have to be louder and or clear.
Can you suggest a few more books other than Goldstein?
Other than Goldstein, so I'll repeat what Prof suggested. One is by Landau and Lifshitz. It's called Mechanics, I think that's the name. It's a very thin and very crisp book. Another is shit, I forgot the name. I'll compile all the names and why don't I show you in the next session because I don't want to
handled
give
Finch,
wrong names. Yeah,
handled Finch analytical mechanics
analytical methods by
and Finch
okay.
and mechanics by Lifshitz and Landau.
Yeah, that's the one I said first. So Landau and Lifshitz. Landau was the professor. Lifshitz was his student, and that's a very nice book. And I think the lectures should generally suffice, but it's always nice to have a book accompanying you.
I have doubt about virtual work.
Yes, please.
So basically why we need it. Like it doesn't happen in real life. So why we always refer as virtual work.
Yes. So if I understand correctly, the question is why do we need virtual work when it never happens? So yes, you are right. First of all, in assuming that virtual work does not happen, in some sense, it is like a hypothetical work. So the idea is that you have some surfaces along which the particle has to move, and that is just a constraint of your problem of your physics. And this means that it could be that net external force could be out of surface, then the surface would provide some force so that the particle respects the constraints of the your system of the problem. And then due to this force, if we assume that the particle is changing its position along the curve, now that will be some work. Now what virtual work is saying is that assume that surface is not changing with time. If you don't change, then in what way can particle move without without not respecting the constraint of the surface? Let's say constraint is that there is an electron which has to be on the surface of this balloon, and now the balloon is let's say expanding. Someone is blowing it. So obviously the electron is going to go away from the center of that balloon. But at a given time, I can ask, where can the electron go? You can think of it as having some superpower so that you can stop time and just move the electron around. So all those displacements would be called virtual displacements, and the work by those forces of surfaces would be your virtual work. Now, can virtual work actually happen? Of course not, because the balloon, as we know, is expanding. So, but this is the thing that this is how virtual work and virtual displacements are defined. The next question is why do we do that? Okay, of course we can imagine that yeah, surface is not moving, fancy, but why? So as you saw, we discovered one important relation called the Lambert's principle in lecture 5, which says that total virtual work done by the surfaces is zero. Um, yeah, so total virtual work is zero, and that enabled us to calculate a quantity, which at the end we called Lagrangian, which obeys some equation that does not refer to this virtual displacement or virtual work anything. So in this perspective, the philosophy is that the concept of virtual work helps us in discovering something that is actually real. So in that way it is useful. So does that answer your question?
Yes, and so does virtual work also help us in predicting the future outcomes of, suppose we take some force on a part, we apply some constraint on a particle and
Yeah.
apply a force on it. So does virtual work helps us understanding the future prediction, future path of the particle?
Yeah, so there are two ways. Virtual work helps us in deriving Euler Lagrangian equation, and from this equation we can predict what happens in future. So not directly, but yes, indirectly, the concept of having virtual work helped us predict what happens in the future, which previously we could not do because of the surface constraint. Okay.
Also, can we derive Euler-Lagrange equation
Mm-hmm.
if we remove the constraints on the particle?
Yes. Yeah, we can. Sure. If there are no constraints, then it becomes actually very easy, because then your coordinates itself are the generalized coordinates because there are no constraints, so all of them are independent. And then the Euler Lagrangian equation just becomes your normal Newtonian equation. F is equal to ma, basically.
Then why we use constraints?
Because in physics we often have some constraint. For example, one constraint is that energy should be conserved, right? If we have a system, closed isolated system, the energy has to be conserved. In some cases, angular momentum has to be conserved. In some cases, charge has to be conserved. So what in physics the general theme is that we want to generalize stuff. So we know as is in high energy, even certain other quantities are going to be conserved. So we want to develop a framework in which this, when we produce these constraints, we can get a newer equation. And Lagrangian is one of those frameworks which allows us to do that. And that's why,
Okay,
yeah, that's why we are pursuing in this direction in advanced mechanics course, because we want to generalize this to higher stuff. Okay.
okay, thanks.
Yeah. Okay. Anyone else?
I have a doubt regarding the degrees of freedom in. I mean, when professor had given an example that says two particles interacting with each other,
Mm-hmm.
force, but their degrees of freedom would still be 6.
So,
Uh,
so
I
which
mean,
which
even if there
system
are
was it?
forces present, um, even if there are forces present,
Yeah.
the degrees of freedom are not going to change.
Right. Right. So here is the thing. Just
Uh,
force does not mean constraint. If you
uh, for,
yeah. So
for,
for
even if the force is specified, I mean, Coulomb attraction is always in a line, right? I mean, connecting those points. If we leave it at a particular initial position and velocity,
mm-hmm.
it will only move move in a straight line, right? So such things are not constraints. I mean, specifications of forces can never be constraints, right?
Right, that's right. Well, you can consider if there are some delta functions in your force. I mean, you can engineer some weird force which can actually impose some constraint. But in general, the natural forces like gravitation and the continuous ones, those will not give any additional constraints.
Oh, can we be more clear upon gravitational? Yeah, I mean, particle in a gravitational field. Why does it have not any constraint?
So, okay, let me just draw a figure. Let's say we have this Earth, so there is a gravitational field around it. Okay. Now, where can the particle be? It can be here, 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 here. Just because
Oh,
there is some force, it doesn't mean a
oh,
particle cannot be in this plane, or it has to be in this plane or this line, right?
oh. Yeah,
Right. So that's the
ah, yeah.
What if it's like the moon, which is locked in orbit with the Earth?
so
Yeah.
so the question is, moon is locked in the orbit. Okay.
So here there will be 2 degrees of freedom, right? For this, or one, because it's
But
moving in a curve.
yeah, yeah. So the curve is not constrained on moon. It's a result of its motion. Like it's not a priori required that moon has to follow. It's not like there is a track that is given and the moon has to follow it. It's a result of the physics that the moon turns out to have an elliptic orbit around Earth. So so the force,
Oh,
yeah. So the force does not require it to be in um, in the orbit a priori, right? For example, if moon had higher energy, it could be in hyperbolic orbit as well, or it could
oh.
fall down
So
towards.
here we are imagining that all of those are variables, right? So those could change.
Yes,
Oh,
so for
oh,
example, energy of the moon,
uh,
so that will give one constraint. That is right here.
Okay. Yeah. I
Okay.
have a question.
Yeah.
So here you talked about here you and the professor talked about mechanical forces for energy. This thing, mechanical systems.
Mm-hmm.
Lagrange is the difference of kinetic and potential energies. So
Yeah.
what if there are non-mechanical systems? Then how will the Lagrangian look like?
Uh-huh. So can you give an example of non-mechanical system?
For example, a circuit with capacitor or resistor or something.
Right. So then what we can look for are analogies. You know the basic equations of circuits, right? So if you have capacitor, then you know how the current changes. If current changes, then voltage changes in this way, that way. Inductor. So in that way, you can draw analogies between them. I do not remember them actually, but you can do something like capacitor is like the mass term, inductor is the friction term,
Okay.
something like that. And using that analogy, you can write the Lagrangian, or
So in that
yeah,
case, the Lagrangian won't be t minus u. It will be something else, like
it can be
c.
something else. Yeah.
Okay.
Mm,
So
yeah.
then the Euler Lagrange equation will also be some other form, or it will be the same form.
So when you write down Euler Lagrangian equation in terms of, let's say, charge and current, then you will find that charge has its own equation of motion, to speak, so to speak,
Right.
and current will
Okay.
have its own equation of motion. And
Okay.
from that, so those are like Newton's laws for circuits, and then
Okay.
we can integrate them to find out what happens in time.
So we don't have to restrict this to only mechanical systems. There
Of
are
course not.
good
Yeah.
analogies to all the different
Yeah.
systems.
Yeah.
Thank you.
Yeah. Okay, anybody else?
One issue I'm facing is like so far with these new concepts of generalized coordinates and virtual work and all this,
uh,
like it's been feeling a bit uh, more abstract. So like, is there a way you could suggest to gain a more concrete understanding of things?
okay, so you can refer to these books. One is Landau and Lifshitz, another is Goldstein. So I'm not sure which chapters. I think in Landau Lifshitz it's in early chapters only. In Goldstein, I'm not sure, but look for the section that discusses this. That is one way. Another general tip would be that whenever you think the things are getting too abstract and wavy sort of thing, it's always nice idea to do more exercises. So you find out these books and do the exercises as well, because the experience helps gain familiarity with the concept, which could otherwise you can find too much abstract.
Okay, thank you.
Okay. Yeah. Anybody? Okay, can some of you introduce yourself? You can volunteer. Okay, then I'll only ask. Meghanath? Meghanath?
Yeah,
Yeah.
yes, sir.
Can you briefly introduce yourself so that I know who am I dealing with here?
So I'm Magnath. Currently, I'm doing my PG in Bardiyar University, Tamil Nadu, Coimbatore.
Okay,
I had completed my UG in PhD College of Arts and Science, Coimbatore.
okay.
Currently, I'm in first year of my PG studies.
Nice. And why are you taking this course?
So I want to learn. I learned Newtonian mechanics in UG. Now I want to learn Lagrangian system. So I take this course.
Okay, cool, cool, perfect. Hmm. Ananta? Ananta?
Hi.
Hi.
Yeah, I'm from Palakkad, Kerala. I'm studying in. I mean, I'm in my fourth year of BTech,
Okay,
Electronics and Communication.
nice.
But
Okay.
yeah, and we don't really have. I mean, real courses in physics in college.
Ah,
But I was so interested in physics. I mean, but somehow I took BTech,
okay.
and I regret that decision right now.
Cool,
I
that's
mean,
not an issue. Physics is
uh,
something anyone can learn, given that
I,
they have interest. Yeah.
I
Yes.
mean, yeah, and I intend to pursue further studies in physics. So I just,
Okay.
yeah, I like physics, so I took this course.
Cool. Cool. Ramai.
I'm from Manipur. I'm doing my BSc in physics, third year.
Okay.
Like, I didn't learn classical mechanics at this Lagrangian Hamiltonian level well earlier, so I'm doing it as a sort of review
Okay.
course.
Nice. Nice. Hope you are safe there.
Yes, I'm safe.
Okay. Dommati Rohit.
Yeah, hello. I'm from Telangana, Varangal, and I'm studying in IIT Billai. I'm fourth year mechanical engineering.
Okay.
I took this course because I'm interested in physics and I want to pursue my master's in physics afterwards.
Oh, nice. Nice.
Sir, actually, I have a doubt in Newton's first law.
Yeah.
As Newton's first law states, in the absence of forces, a particle moves with constant velocity v.
Mm-hmm.
So, if we take a circuit
Mm-hmm.
and a closed circuit,
Okay.
and if we just cut the wire,
Mm-hmm.
so then why don't the electrons come out of the wire? Because they need to follow the inertia, no? According to Newton's first law.
Okay. But imagine you. So first of all, you omitted one important term, that is inertial frame. Only in inertial frame, when you have net force is equal to zero, particle moving in with constant velocity. But I think you had it in your mind, just did not. So I just thought I should point it out. Now imagine you are an electron in a copper wire that is cut.
Okay.
So if you try to escape, what will happen? Is, are you not feeling any forces? What will be around you? So you will find lots of other electrons around you of copper.
Yes.
Then you will find neutrons and protons, the nuclei, right?
Yes.
So what's the force on me? The force on me is the force due to all the electrons and the neutrons and the protons. Now, due to neutrons, it would be zero, at least the electrostatic one. So, but from the protons and electrons, I still have force, right? And that need not be zero. So why should it
Yes.
go to? Why should it just escape?
Okay.
Okay, you understand. So just
Yeah, I got
because
it.
we are cutting the wire doesn't mean the electron now feels nothing.
Huh.
Okay.
Okay.
Yeah, cool. Elizabeth.
Hello, I am Elizabeth Santosh. Currently, I am doing my MSc from SB College Chakanashiri. I am attending this course because I think that I need to improve more in this or that.
Okay, fair enough. Yeah, nice. Okay, and Harish.
Hello, bro. B.Tech student.
You are not audible.
Am I audible right now?
Now it's better. Yeah.
Yeah. So I'm Harish. I'm doing my B.Tech in mechanical engineering at NPTEL.
Okay.
Plan to switch to physics, so I thought let's give it a go to classical mechanics in the first.
Okay. Nice. Nice. Cool. Okay. So I think today you should have got the flavor of what kind of sessions these are going to be. Um, so this is a program between PMRF and NPTEL. So we essentially get paid for this. So it's up to you that you make use of these sessions. These were not previously available, say 2 3 years before. So now that you have it, I think you should make use of this as much as you can in the upcoming sessions. If any, okay, anybody has any questions, comments, suggestions? Is the timing okay with everything?
Yes, the timing is perfect.
Okay, yeah. And anyways, if
I
you
know.
miss one of them, then you can always go to YouTube and see it later.
I know which area do you work.
Sorry.
Like I know the work you do as a PhD student.
Oh, the field I work in is PhD.
Yeah.
Oh, so I work in experimental nonlinear dynamics. So, as you might have heard of chaos theory, so I do something related to that. Actually, the system I use is human brainwaves. So we take data from human brainwaves and we try to modify them. And using that, we try to learn how physics of brain works, basically. So it's an interesting thing and kind of an extension of this course, you can say.
Yeah, that sounded really interesting.
Yeah.
Are we by chance going to touch upon any chaos theory or perturbation theory here? Because in my college, in our classical mechanics course, we had a bit of that.
I don't think so because if you look at a professor's introduction lecture, that is lecture 0 on YouTube, he says he will not venture into either chaos theory or this any advanced stuff. Yeah. So I think not. Yeah. But if you have any particular question in nonlinear dynamics or chaos, you can ask me in one of these sessions. That is fine.
Sure.
Okay. Anybody else?
Could you kindly repeat what you're currently doing? I mean, my network is gone. So
So I work in the field of experimental nonlinear dynamics. Nonlinear
oh
dynamics is also called chaos theory popularly.
oh
The system I have is human brain, so we try to modulate human brain waves and try to learn what happens in the brain.
so where are you currently working?
At IIT Bombay.
Oh,
Yeah. Okay. If there are no questions or anything, we can say goodbye. If there are any questions, let me know.
so
Anyone?
where have you
Yeah.
studied earlier?
I did my bachelor's and master's in ISC Bangalore
Oh,
with physics major.
oh, oh.
Okay. Any further question?
In which channel will these recordings be available, by the way? I attended another session, but I was not sent any details for the recordings.
Yeah, so maybe you'll join later. My name is Arsh Chotalia. This is the name of the channel. It is very popular one. It has got 1 subscriber, so maybe you can increase it. This is the QR code. You can take screenshot of anything.
Okay, thanks.
Right now I am traveling. Actually, I am in IIT Madras for a conference, so I may not get internet to upload. So within 2 or 3 days, I should be able to upload. Next week onwards, it should be almost instantaneously. Okay.
Are there any ways to contact you? I mean, for
Yeah. So this is my email, rchotalia@iitb.ac.in. Send me an email with, just put in subject NPTEL course or something, so that I know it's regarding this. So,
okay.
yeah, if you have any questions, if you are trying to solve something from some book and you're not able to, just send me. I won't be able to send you solutions then, but we can discuss it in one of these sessions.
Oh, okay, okay.
Okay. Yeah. Okay. So, uh, Sakti, hi Sakti, you just joined. Is that right? Hello, Sakti. Am I audible? Okay, she is showing some Sakti. But okay, then if there are no questions or anything, we can leave. Okay, we'll meet next Tuesday at 6 o'clock, and bring your questions. Send me your questions if you have any, and hopefully next week we'll have even more interaction. Okay, so I'll stop sharing and bye.
Bye.
Bye.